Welcome. This is a video presentation of the paper, The Origin of Matter and Gravity, What They Are and Why They Exist. Part 2. Matter is created to conserve angular momentum and centripetal force. A centripetal force is a force that makes a body follow a curved path. The direction of the force is towards the instantaneous center of rotation. The word centripetal means center-seeking. Angular momentum is the rotational version of straight-line linear momentum, product of the mass times the velocity. Angular momentum, given as L, is a product of the moment of inertia times the angular velocity, where I, the moment of inertia, is a product of the constant k, the mass of the object, and the radius squared. Now the constant k here is the moment of inertia constant, or inertial constant, and it depends on the mass distribution. And in our case, for a while here on this video, we're just going to define k as 1. Omega is equal to the tangential velocity divided by the radius. So we can take our values and we find that L is equal to I, which is the mass times the radius squared, and we've set k equal to 1, so that's not a factor, times omega, which is the tangential velocity divided by the radius, and the radiuses cancel out. So we get mass times radius times tangential velocity is equal to L. Let's look at the initial angular momentum. L sub I, or L sub initial, would be equal to the mass times the radius times the tangential velocity. The initial mass, as we've seen particularly in the paper on the geometric mean expansion, is the Planck mass divided by 2. Our initial radius is 2 Planck lengths, and we've defined the tangential velocity from the time paper in particular as the square root of 2 times the speed of light, c. So the product of the three gives us the initial angular momentum of square root of 2 times h bar. Let's now look at the initial centripetal force. F sub c is our centripetal force, and it's equal to the product of the mass times the angular acceleration. So this is our initial mass. Acceleration is v squared, which is square root of 2c squared, so we get 2c squared, divided by the initial radius, and so we get the Planck mass divided by 2, our initial mass, times 2c squared over 2lp, and this works out to be c to the 4th divided by 2g. And you'll notice that this value here is 1/2 the Planck force. This is the initial Planck force. In the geometric mean paper, we saw that the angular momentum of the observable universe is increasing. Each doubling of the radius of the hyperverse increases angular momentum 4 times. Using our now and then approach that we've used previously, we find that the ratio is 4. So the angular momentum of the universe now versus when the radius was half of what it is now is increased by 4 times. And so let's look at the angular momentum of the observable universe. L sub O is equal to mass times the radius times the tangential velocity. This is our mass of the observable universe. Hyperverse radius is the radius, and it has a constant value for the tangential velocity of the square root of 2 times c. And the product works out to be the square root of 2 times h bar times r sub h over 2lp squared. That's the large number that we talked about so much in the geometric mean paper. Looking at the centripetal force of the observable universe, F sub c, we'll take the product of the mass of the observable universe times the velocity squared, 2c squared, divided by the radius. The product works out to be c to the 4th over 2g. And our product, c to the 4th over 2g, is the conserved initial value. The geometric mean counterpart of the angular momentum of the universe is given by, we'll call it L sub s, and using the geometric mean type equation, it'll be the initial angular momentum squared divided by the angular momentum of the observable universe. And we saw that the initial angular momentum was the square root of 2 times h bar, so we square it. And we'll divide that by the square root of 2 times h bar times the large number, which is the angular momentum of the observable universe. And it works out to be the square root of 2 times h bar times 2lp over r sub h, quantity squared. And our value here matches the value we get using the geometric mean counterparts of small mass and small radius. So our geometric mean angular momentum is equal to the product of the small mass, put an m, small radius times our tangential velocity, and we get this value here, and they're the same. Looking at the centripetal force of the geometric mean counterparts, we find that F sub c, centripetal force, is equal to the mass of the small energy quantum times the tangential velocity squared divided by the radius of the small radius quantum, and we get c to the fourth over 2g. This is our conserved initial centripetal force. Looking again at angular momentum, we see that the angular momentum of the geometric mean counterparts is equal to the square root of 2 times h bar divided by the large number. The angular momentum of the observable universe is equal to the square root of 2 times h bar times the large number. And can't say if this is really important or not, but it's certainly noticeable that if we were to multiply these two and take the square root and get the geometric mean, we would find the initial conserved value. Interesting also is that if we take our geometric mean angular momentum, up here our square root of 2 times h bar times 2lp over r sub h, quantity squared, here, and multiply it by the number of SEQ, small energy quanta, we get the conserved value. Now we're looking at the SRQ, the small radius quantum. The angular momentum of one small radius quantum is equal to the mass of a small radius quantum times the radius of the small radius quantum times our constant tangential velocity. So the mass of the small radius quantum, again, is the mass of the observable universe divided by the number of small radius quanta within the observable universe times our radius times the tangential velocity, and we get the square root of 2 times h bar times 2lp divided by r sub h to the 6th power. The angular momentum for all of the small radius quanta is the product of the angular momentum of one small radius quantum times the number of them in the observable universe. So our value here is the same as this. It's the angular momentum of 1, and there are r sub h over 2lp to the 6th power, or the large number cubed, units of small radius quanta. And the product of the two gives us the conserved angular momentum, the initial value. Looking at the centripetal force for one small radius quantum, we take our equation, F sub c is equal to the mass of a small radius quantum times the tangential velocity squared divided by the radius of the small radius quantum. And it works out to be c to the fourth over 2g times 2lp over r sub h to the 4th power. Our product, or result, for the centripetal force for the small radius quantum is not the conserved value. And even if we multiplied it by the number of SRQ, which is the large number cubed, we still don't get the conserved value. So at the SRQ level here, we have a problem. But we'll be coming back to this. Looking now at the small energy quantum, the SEQ, we find the angular momentum of one SEQ is equal to the product of the SEQ mass times the SEQ radius times the tangential velocity, and we get the square root of 2 times h bar times 2 Planck lengths divided by r sub h to the 2/3 power. Our value for the angular momentum of one small energy quantum is not the conserved value. And there's a large number of them, r sub h over 2lp squared. And we multiply this value here times the number, and we get the square root of 2 times h bar times r sub h over 2lp to the 4/3 power. Angular momentum is not being conserved at the small energy quantum level. So we have a problem here too. Looking at the centripetal force of one small energy quantum, we find the mass of the small energy quantum times our constant tangential velocity divided by the radius of the small energy quantum. And we get the centripetal force is equal to our initial conserved value, c to the 4th over 2g, times 2 Planck lengths over r sub h to the 4/3 power. So we don't see conservation of centripetal force at the SEQ level. And looking at this further, even if we take the centripetal force of one small energy quantum times the number of SEQ, we get c to the 4th over 2g times r sub h over 2lp to the 2/3 power. This is not working. The SEQ will not conserve centripetal force. Here's a summary of what we've seen so far. It's good to look at it because we've been kind of all over the map. This column represents angular momentum, and this column is our centripetal force. In the initial state, our angular momentum is the square root of 2 times h bar, and the centripetal force is c to the 4th over 2g, 1/2 the Planck force. For the observable universe, we see that angular momentum is quite large, and we talked about it in the previous paper that it looks like we have a runaway angular momentum. Despite that, though, it's conserving the centripetal force. We'll jump down here. The small radius quantum. Interestingly, the angular momentum of all of the SRQ is the conserved value. And for all of the SEQ, it doesn't work. It doesn't work for the SEQ at any level, except one kind of peculiar one. That if we take the angular momentum of the geometric mean counterpart and multiply it by the number of SEQ, we see that in a kind of a false way that the small energy quantum, not this, but here, has this conserved value. So it's as though the small energy quantum is working as an active agent in the geometric mean counterpart equation to conserve angular momentum at the SEQ level, much in the way that we see angular momentum being conserved at the SRQ level by itself and inherently. Looking at the centripetal force, we see that the initial state is conserved, the observable universe conserves it, and that interestingly conserved by the geometric mean counterparts. But we do not see conservation of centripetal force at any of the quantum levels. They're all off. We see that the universe appears to want to conserve angular momentum and centripetal force. But a problem exists at the quantum levels, at both the SEQ and SRQ levels. Looking at elementary particles, we find that they have an intrinsic angular momentum, or spin. For a spin 1 particle, the spin angular momentum, big S, is equal to the square root of small s times small s plus 1 times h bar. S is the spin quantum number. And if it's 1, we find that the spin angular momentum is equal to square root of 1 times 1 plus 1, which is 2, times h bar. So we find that the spin angular momentum is equal to the square root of 2 times h bar. And this value is our conserved initial angular momentum. And we find also that elementary particles also conserve centripetal force. Using our equation for centripetal force is equal to mass times the angular acceleration, and inserting our values of the ideal mass and ideal radius, we find that the centripetal force of a particle is equal to c to the fourth over 2g. And this value is our conserved initial value. We will make the claim that the universe creates elementary particles in order to conserve both angular momentum and centripetal force. Looking at the small energy quantum, we find that the angular momentum, as we've seen for 1 SEQ, is equal to the square root of 2 times h bar times 2lp divided by r sub h to the 2/3 power. Now, if we packed r sub h over 2lp to the 2/3 power, that number of SEQ into the volume of 1 SEQ, angular momentum would be conserved. So we take our value for the angular momentum of 1 small energy quantum here, and we'll multiply it by r sub h over 2lp to the 2/3 power, and these cancel out, and we get our conserved angular momentum. And our cube diagram might help visualize this. The large number, r sub h over 2lp squared, can be split into 3 sides on a cube, each side being r sub h over 2lp to the 2/3 power, and the product of these 3 would be r sub h over 2lp squared. Now the blue here, representing the bottom, is the number of elementary particles. We would just take one side times another side, and it gives us r sub h over 2lp to the 4/3 power. That's the number of particles in the observable universe. And what we're saying is that if we take a column at any point and crush it all the way down and put all of the SEQ that are along that dimension down in to the bottom, we would have the conserved angular momentum. Packing in r sub h over 2lp to the 2/3 units of SEQ into the volume of 1 SEQ conserves angular momentum, but it does not conserve the centripetal force. F sub c, our centripetal force, is equal to mass times the angular acceleration. And the brackets here is the mass. We'll take the mass of 1 SEQ times the number that we're packing in, multiplied by our tangential velocity squared, divided by the radius of the SEQ. And we find that the centripetal force is equal to c to the fourth over 2g times 2lp divided by r sub h to the 2/3 power. However, we can conserve centripetal force if we shrink the radius from the SEQ radius to the geometric mean of the SEQ radius, which is the radius we claim is the particle radius. So, we take our centripetal force, and that's equal to the mass times the angular acceleration, and our mass of a particle, which equals the mass we just saw, which is h bar over c times r sub h times r sub h over 2lp to the 2/3 power, which is the number of SEQ that we're compressing into the radius here, and we get our conserved value. In shrinking the radius to the ideal particle radius, we appear to have changed the angular momentum as such. We have our mass, our SEQ mass times the number of SEQ we're compressing, times the radius, our particle radius, times our tangential velocity, and we find that the angular momentum is now less than the conserved value by a factor of 2LP divided by RH to the 2/3 power. But we're going to claim that the angular momentum has not changed. Angular momentum technically is given by the equation of L is equal to the mass times the radius times the tangential velocity times a constant k, where k is the moment of inertia constant. But we will come back to this after first looking at the small radius quantum. Let's look at the SRQ, or small radius quantum. The small radius, the radius of the SRQ, is actually smaller than the particle radius. Our particle radius, given by the figure here, is 1.6 times 10 to the minus 55 meters. The radius of the SRQ, 4 times the Planck length squared divided by the radius of the hyperverse, is approximately 3.98 times 10 to the minus 96 meters. If we take the ratio of the radius of the small radius quantum to the particle radius, we get 2LP divided by R sub h to the 2/3 power. We find that the SRQ radius would have to expand its radius to fit into a particle radius. Now there are R sub h over 2LP to the 4th small radius quanta in one small energy quantum. And there are R sub h over 2LP to the 2/3 power worth of SEQ in a particle. So we find that the centripetal force is equal to the mass of one SRQ times the angular acceleration, and that's the tangential velocity squared, divided by the radius of a particle, times the number, we see here, of SRQ in one SEQ, times the number of SEQ in a particle, and we get the conserved initial value. So we can conserve centripetal force by coalescing R sub h over 2LP to the 2/3 units of small energy quanta into the volume of the particle radius, or geometric mean of the SEQ radius. And this works for both the small energy quantum and the small radius quantum. Our angular momentum values appear to change, though. We'd achieved the conserved value, the square root of 2 times h bar, when the radius was the small energy quantum radius. Shrinking the radius to the particle radius altered the angular momentum. We're going to look now at the SEQ. And by native SEQ, we're referring to the small energy quanta that are unaltered, basically the SEQ of open space. And within the volume of one SEQ, the angular momentum, as we have seen, is the mass of one SEQ times the radius of the SEQ times the tangential velocity times the number of SEQ that are within the SEQ volume. And we saw that we had the conserved value. Now, the section down here shows what happens when we compress it not into the SEQ radius, but shrink it into a particle radius. And the result is a decrease to the square root of 2 times h bar times 2LP divided by R sub h to the 2/3 power. And looking at the SRQ, the small radius quantum, shrunk within an SEQ volume, we get the conserved value, the square root of 2 times h bar, taking the mass of the SRQ times the SEQ radius times the tangential velocity times the number of, in this case here, the number of SRQ within one SEQ and the number of SEQ within the particle. And down here the section shows the same sequence, but instead of the small energy quantum radius, we've shrunk it down further to the particle radius, and we see we have a decrease of the angular momentum, the square root of 2 times h bar times 2lp over r sub h to the 2/3 power. This is the same decrease we had with the SEQ. So again, we've seen that both the SRQ and SEQ have the same factor of difference. And if we multiply the angular momentum of either the SEQ or the SRQ by this factor, r sub h, or 2lp to the 2/3 power, we would get the conserved value, or keep the conserved value. Now we will address the k value in the angular momentum equation, where angular momentum is equal to mass times radius times velocity times k, where k is the moment of inertia constant. K is related to the distance the mass is from the axis of rotation. If all the mass is at an equal distance from the axis of rotation, then k is equal to 1. If the mass is within this distance or radius, the k value will be less than 1. But if the mass is outside the radius, the k value will be greater than 1. We have defined k equals 1 for native space, space in its unaltered original form. Let us now see why this is the case. Let's look at the moment of inertia, I, for a thin circular hoop. And here we have our thin circular hoop, the center, and this is going to be our axis of rotation. It runs through the circular hoop, kind of like a finger through a ring. So all of the mass is on the circumference here, on the edge of the hoop. The moment of inertia, in this case, is the mass times the radius squared. This is the same equation that we use for the hyperverse. All of the mass is at an equal distance from the axis of rotation. And our k value is equal to 1, our moment of inertia constant. Now let's look at a hollow, spinning sphere. Kind of like the way we're describing the hyperverse. We have our sphere, and it's hollow. There's nothing in the center. All of the mass is on the surface. The axis of rotation, we're going to run from top to bottom. The radius goes from the center to any point on the side. And if we see that as the forward part, that would be the radius, and this is looking through it, that would be the radius as well. The moment of inertia, I, in this case, is equal to 2/3 times the mass times the radius squared. And this 2/3 is our k value, and it's less than 1. And this is because the mass is not all at an equal distance from the axis of rotation. We have at the equator our maximum distance, but at the poles, for example, we have essentially from 0 to ever increasing distance from the axis of rotation. Unlike the circular hoop, in the case of a sphere, some mass is closer to the axis of rotation than other mass. So a k value is not 1, but less than 1. Now let's look at the hyperverse. We say that it's hollow and there's spin, but the spin is different. The spin is quantized on the surface. So we have a surface of the hyperverse, and that's where the universe is. The center is hollow. There's a radius from the center of the hyperverse to the surface. But what we're saying is that the surface is composed of vortices, something that mimics vortices. So the entire surface has vortices on it, and they have spin. And this is supposed to be on the surface. So the distance from the center to any point on the surface is identical. And there is no axis of rotation. So the moment of inertia, I, is equal to the mass times the radius squared, because k is 1. All the mass is at an equal distance from the center, and without an axis of rotation, there is no variation of mass being distributed from the center. There's no North Pole or South Pole. You could turn this thing any way you want, and you would have the same shape or same spin orientation, because the spin is linked to individual points on the surface. So we're able to make the claim that the k value is 1, and even though it's a spinning hollow sphere, the moment of inertia is still mass times radius squared. The hyperverse is not a spinning sphere. Each point has spin, its own spin, as the surface is composed of individual units. There is no axis of rotation, such as a line running from a north pole to a south pole. And since all of the mass is at an equal distance from the center, we can make the claim that the constant is equal to 1, and that the moment of inertia is therefore simply the mass times the radius squared. And we assume self-similarity, that is, the quanta are like the whole. So we've defined that k is equal to 1 for a native space in its unaltered original form. But we're going to make the claim that compression of the small energy quanta and expansion of the small radius quanta changes the mass distribution in relation to the radius. Notice that the ratio of the small energy quanta to the particle radius is identical to the ratio of the particle radius to the small radius quantum radius. Both ratios equal the same value, r sub h over 2lp to the 2/3 power. And what we find is that the particle radius is actually the geometric mean of the small energy quantum radius and the small radius quantum radius. That is, we'll multiply the small energy quantum radius by the small radius quantum radius, and we get the particle radius squared. And we've seen some time ago, and we use it a lot, that the particle radius is the geometric mean counterpart of the small energy quantum radius against the initial radius. That is, if we take the initial radius squared and divided it by the small energy quantum radius, we get the particle radius. So we have an example here of the particle radius being the counterpart for the small energy quantum radius against the initial radius, but it also happens to be the geometric mean of both the small energy quantum radius in the small radius quantum radius. And let's look first at the change that occurs with the small radius quantum. We have here the small radius quantum. The radius is here, and this would be our native radius. With expansion of the SRQ up to the size of a particle radius, the mass, which is on the surface here, will move out to this position here. But this is a small radius quantum, and we're going to make the claim that, mathematically at least, the radius stays unchanged. So we find that the mass moves out beyond the radius. In this slide, we're going to look at the SEQ shrinking down to the particle size. Our SEQ radius is here, and our mass is on the surface. With shrinkage, we're going to make the claim that the radius changes its position and shrinks to here, but it's going to act as though the mass is still here, because this is the small energy or small mass quantum. And in this particular case, we find again that, mathematically at least, the mass is placed outside of the radius. So we're going to make the claim that shrinkage of the small energy quantum down to the particle size, that the radius shrinks relative to the mass or energy, and that the energy is constant. Expansion of the SRQ up to the size of a particle, we find that the mass or energy expands relative to the radius, and that the radius is constant. So we see the dominance of energy in the small energy quantum, because with change, alteration, in this case shrinkage down to the particle size, we find that the energy or mass appears to stay in a constant value. Whereas the SRQ, the radius is dominant. So it's the mass or energy that expands relative to the radius, and the radius maintains its constancy. The mass lies at a distance of r sub h over 2lp to the 2/3 power times the radius from the center, so that the k value is equal to r sub h over 2lp to the 2/3 power, precisely countering the shrinkage effects. The angular momentum remains at the conserved initial quantity of the square root of 2 times h bar during particle formation. So using our equation of the angular momentum equaling the mass and the radius and the velocity times the moment of inertia constant, k, we can insert our mass, which is the same whether we consider the SEQ or SRQ, times the particle radius, times our tangential velocity, times the k factor. And the result is the angular momentum is equal to the square root of 2 times h bar. Angular momentum is conserved. The universe is able to conserve its angular momentum and centripetal force at the quantum levels by creating particles of matter. Matter is concentrated space, forced to coalesce and change from its native state to conserve angular momentum and centripetal force. This explains why all particles of a kind are the same everywhere. If any more or less quanta of space collapsed to create a particle, then the angular momentum and centripetal force of the particle would vary from the target value of the square root of 2 times h bar. Space collapses to the point that the angular momentum and centripetal force matches the initial conserved values. This collapsed and coalesced space is matter. It is a beautifully simple system that produces identical particles of a kind everywhere in the universe, and one that produces the number of elementary particles that we find in the universe. It is a universe-wide, self-regulating mechanism that determines the size and number of elementary particles. And it gives us much more. Look at the equations of the ideal particle, and you will see that matter is not static. The characteristics of matter change with time or radial expansion. We see the radius of the hyperverse is included in each of these quantities. So as the radius of the hyperverse gets larger, the particle radius is going to drop down. The particle mass will decrease, and the particle number will increase. Look at the equations of the small energy quantum and the small radius quantum, and you will see that the quanta are not static either, as they also change with expansion. The energy of the small energy quantum will decrease with expansion. The energy of the small radius quantum will decrease with expansion. And even though a few slides ago we saw that the mass of particles decreases with time, particles are composed of quanta, and the quanta are shrinking at a faster rate than are the particles. We see here, as we've seen numerous times, our now and then approach. And particle mass, with a doubling, shrinks by about 0.8. The SEQ mass shrinks at 0.5 with a doubling. The quanta are shrinking at a faster rate than the particles are. And this difference between the shrinkage of a particle mass and the shrinkage of its component quanta requires that the particle continue aggressively absorbing the quanta of space. The universe continues to expand. The angular momentum of the universe continues to increase, and particles of matter must continually form and accrete the quanta of space to conserve angular momentum and centripetal force. All of this leads directly to gravity, which we will see as the ongoing accretion of space by matter.